Suppose you need to integrate some rational function, and let's assume that rational function, and we'll call it capital F of x, is in the form of f of x over g of x, where f and g are polynomials. Okay, well, one way to integrate that function would be to rewrite f of x over g of x as a sum of multiple terms by decomposing that fraction. And so the rules here for finding partial fraction decomposition here is given right here. Now, we're not going to worry about the first rule for now, but basically the first rule just says if the numerator is not lower than the degree of the denominator, then you could actually divide the denominator into the numerator by using long division, and then you could actually rewrite the fraction. But on our problems, we're going to assume that we're going to start out with problems where the numerator does have a lower degree than the denominator. Okay? So now the trick here is actually to express the denominator as a product of linear factors px plus q, or irreducible, that just means they can't be factored, quadratic factors. And then also we're going to have, if we have repeated factors, we'll have more terms. And so let me just show you how this works. So I'm going to start you on this case I call 3a here. In 3a, we're going to assume that all we have are linear factors. And if we have linear factors, then for every linear factor we have, we're going to write the rational function as a constant over each linear factor. And then if the linear factor is raised to a higher power other than 1, then for each power that our linear factor is raised to, we will actually add another term up into. So in other words, if this was px plus q cubed, we would write a constant over px plus q plus a constant over px plus q squared, and then plus a constant over px plus q cubed. Okay, and of course if there were other factors of a different linear factor, then we'd also have to have terms for those as well. So let me show you how to do part 3a here. Okay. Now I'm just gonna show you how to break these fractions up, and then I'll show you how to put them in put them in the integral, and then to integrate this, because the whole point of all of this is that we want to know how to integrate this rational function, and we don't really have a good way to integrate it right now. So what we can do is we can write this as a sum of other fractions. So that's the idea. Now, so the trick here, notice this one's already factored in the denominator. You have x plus 1 times x minus 3. So since each of these is raised to the first power, I'm going to have one term for each of these. So for the x plus 1, I'm going to have a term a1 over x plus 1, and for the x minus 3 factor, I'm going to have a term b1 over x minus 3. So I know that this fraction can be written as the sum of those two terms. I just have to figure out what is the a1 and the b1. What are those constants? Now, one easy way to simplify this is to multiply both sides by the lowest common denominator. Now, the lowest common denominator of these terms is simply x plus 1 times x minus 3. Now, if you multiply the left side by x plus 1 times x minus 3, that's just going to limit the denominators. And so what you'll get there, notice down here, you'll just get 5x minus 3. But now, if you take this same pair of this same product here, and you multiply it by a1 over x plus 1, if you multiply it by this term, then the x plus 1's cancel, and you'll have a1 times x minus 3. And so notice that's what I have here. Now if you multiply this by the second term, then the x minus 3's cancel, and you'll have b1 times x plus 1, which is what I have here. Alright, now So on the left-hand side, I have 5x minus 3, and on the right-hand side, I have these two expressions. Well, let's go ahead and distribute a1 through. So we get a1 times x, and then a1 times minus 3. So we get a1x minus 3a1. We'll also distribute here, b1x plus b. Now notice that I have an a1 term here that has an x with it, and I have a b1 here that has an x with it. So let's put the like terms together here. So we'll put those terms together. And then after we put them together, I don't know why I copied that a second time, but anyway, after we put them together, then we can factor the x out. Okay, now notice the coefficient of x on the right-hand side is a1 plus b1. And the coefficient of x on the left-hand side is 5. So then a1 plus b1 must equal 5. So that gives me this equation. All right, now look at the constants. The constants are minus 3a1 plus b1. Those are just constants. So minus 3a1 plus b1 has to equal the constant that I have on the left-hand side. So minus 3a1 plus b1 must equal negative 3. So what we have to do is, now we have to solve this system of equations. Now, as a calculus student, you should know how to solve systems of equations by either substitution or elimination method. So I'm going to leave that to you. But if you solve this system of equations, you're going to get a1 is equal to 2 and b1 is 3. And then, remember I said that I could write this fraction as the sum of these two terms where a1 and b1 were their numerators. Well, so let's put a1 in the numerator of the first term and b1 in the numerator of the second term. And now we've rewritten this. In other words, we've decomposed this fraction into its sum of partial fractions. So the two fractions are 2 over x plus 1 and 3 over x minus 3. Now, how is that helpful? Well, here's how it's helpful. If we wanted to, just a minute here. All right, so if we wanted to integrate this function, well, we could actually rewrite that function as the sum of those two partial fractions. And then we could integrate each of those partial fractions. And I'm not going to go into that. You should know how to integrate those by now. Just let u equal the denominator in each case, and you'll actually get that those two integrals will integrate to 2 times natural log of the absolute value of x plus 1 plus 3 times the natural log of the absolute value of x minus 3. And then throw in your constant, and you're done. So you see, by breaking this fraction up into these two partial fractions, it gives us something that we know how to integrate. Now, on this second example, I'm not going to go into the details here, but you're welcome to freeze the video and study it a little more closely than what I'm going to talk about here. But notice that if you rewrite the denominator here, you get x times x plus 3 times x minus 1. So since I have 3 linear factors here, then I must be able to break this fraction down into 3 partial fractions. And so the first term would be constant over x, and the second term would be a constant over x plus 3, and the third term would be a constant over x minus 1. Now, whether you use a, b, and c, or whether you use a1, b1 doesn't really matter. You're just picking a letter to represent these constants. Okay, now let me just go ahead and tell you the least common denominator of those fractions is x times x plus 3 times x minus 1. And if you multiply on the left, you'll just get the numerator. And if you multiply each term on the right, you'll get what I have here. So I'll let you do that, but that's what you'll get. Okay, now, so what I can do now is I can simplify the right side. So go ahead and FOIL here, distribute here, and then multiply. After you FOIL here, multiply by a, and after you distribute on these two, multiply this by b and this by c, and then you'll get this right here. And notice that you have 3 terms with x squared in it. You have ax squared plus bx squared plus cx squared. So you can factor the x squared out, and you get a plus b plus c. Well, that has to equal the 4. That's got to equal that 4 there, because that's the coefficient of the x squared term. And then if you put all your x's together, you'll get 2a minus b plus 3c times x. And so this sum has to equal the coefficient of x, which is 13. And then the only constant you got is minus 3a, so minus 3a has to equal negative 9. And so then you can solve this. Well, you can easily solve this for a, and you get a equals 3. And then you can plug the 3 back in here for a in both of these equations, and then you can solve these equations for b and c by solving the systems of equations. So now, since I know a, b, and c, I know that the first fraction is 3 over x. The second one is actually minus 1 over x plus 3 because I solved it and got b equals negative 1. And then the third fraction is c equals 2, so that's 2 over x minus 3. And then what you could do then is you could actually rewrite this fraction. If you had to integrate this function, you could actually rewrite this function as those three functions and then integrate those three functions separately, and then you would get your result for the integral. So that's what these are meant for, to simplify rational expressions so that you can integrate them much easier than you could if they were left in their original form. Okay, this next one shows you what to do if you have repeated linear factors. So here I have x plus 1, so I'll go ahead and write a over x plus 1. But since I have x minus 2 quantity cubed, I'm going to write that as b1 over x minus 2, b2 over x minus 2 squared, and b3 over x minus 2 cubed. So you got to have a term for each power that the x minus 2 is raised to. Now, the lowest common denominator of all of these fractions would be x plus 1 times x minus 2 quantity cubed. Now, I'm going to assume that you kind of got the hang of this now. So if you multiply the left-hand side by x plus 1 times x minus 2 cubed, it just gives you the numerator. And then if you multiply this times this term, the x plus 1 cancels and you get this. If you multiply it by this term, the x minus 2 cancels and you get this. If you multiply it by this term, the x minus 2 quantity squared cancels and you get this. And if you multiply it by this term, the x minus 2 quantity cubed cancels and you just get this. Now on this example, I wanted to show you a different method. So here we have all of this. So let me just tell you, because I'm going to have to speed this up a little bit. What I'm going to do is I'm going to let x equal 2 in this equation, and then watch what happens. If you let x equal 2 over here, just plug 2 in for x, you'll get 6. If you let x equal 2 here, all of these terms will disappear. So this term will disappear, this term will disappear, this term will disappear, and so you will get b3 times 2 plus 1, which is 3b3. So then you can solve for b3 and get b3 is 2. If I let x equal negative 1, then all of these terms would disappear. And if I plug negative 1 into the left, I'll get negative 54 on the left. And then if I plug negative 1 in here, I'll get negative 27. So I get negative 27a, and then divide both sides by negative 27, and I get a equals 2. So I got a and b. The next thing I'm going to do is I'm just going to let x equal 0. So let x equal 0 and plug that in. Now remember, anywhere there's a b3 or an a, you already know what those are. So go ahead and plug those in. And basically what you'll get there is you'll get an equation, 4b1 minus 2b2 equals 10. Now do the same thing, but let's let x equal 1. And then if you put 1 into the left, you'll get 10. And if you put 1 on the right-hand side, you'll get 2 plus 2b1 minus 2b2. And then we have that equation. And if you put those two equations and solve them, you'll get that b1 is 1 and b2 is negative 3. So now we have all four values, and we can actually write our fraction as a sum of four terms, because we know a, we know b1, we know b2, we know b3, and now we can break this up and integrate it term by term. And on this, all you have to do, the first two integrate using log properties, and the second two integrate using the power rule, and you get your final answer. And so that's how you deal with linear factors. In the next video, I'm going to show you how to deal with those irreducible quadratic factors.